Alright, so the area problem, as the previous video touched on, kind of like the rate of change problem, it's simple. Rate of change, I know it exists, but it was hard to find, right? It's a special type of limit. Same thing here. I can visually see there's area under that curve. But it's not easy to find, because there's not a nice geometric formula that allows me to solve for it. So just like with the rate of change, we went back to the average rates, which I can find, and took a limit of it. Something similar is going to happen here with area. Alright, so what we do is we're going to calculate the accumulated area of a region bounded by a positive. Alright, I'm going to find out total area, the accumulated function area, bounded by my function and my x-axis, and it is related to the x-axis. It's between the function and the x-axis. So in general, what we do is, well, since I can't find it with a formula, a geometric formula, we break it down into one we can solve. Right? Break it down into a formula we can find. And so what we do, well, what's the easiest geometric formula? Well, the easiest geometric formula is it's rectangle, right? And so that's what we do. So we take our total region and break it down. All right, so I'm going to do this in an example. So I'm going to look at a simple example. So I've got my function here, which represents x squared plus 1 from 0 to 2. All right, so I want to find the area of the shaded region here, which again would be my function f of x squared plus 1 from 0 to 2. So it's this green area here, right? The bounded by my function and the x-axis, right? Total area here, which it's sort of trapezoid, but it's not because there's a curve to it, all right? So again, you could approximate it using a trapezoid, but I don't want to. We're going to use the method that we're going to get to the fundamental theorem of calculus here. All right, so again, I can't find this area exactly right now. We're going to eventually get to that, where we will. But what we're going to do is we're going to estimate it by finding rectangle areas to approximate it, right? Rectangles are simple, easy areas. So instead of looking at the total region, we're going to break it down into small little areas, all right? Dividing up the area. And so what we do is we'll divide up the area, take my change in x. My change in x would be going from x equals 0 to x equals 2, right? That's my change in x. This would be my a, this would be my b, right? I'm going from 0 to 2. That's my total area that I'm looking at, from 0 to 2. And so my change in x would be, well, I would take my 2 minus my 0, and I divide by how many rectangles I'm going to draw. And I want them to be equal width. So this delta x represents, I'm breaking it down into small area regions of the same width. Not the same height, the same width. Alright, so each individual so I'm going to draw rectangles. Each individual rectangle will have the same width, but different heights. The heights will be found using the function. Alright, that's what the heights will be at a specific point. Now the problem is there are actually infinitely many ways I can draw my rectangles. Now there are two common ways that we can draw it, which is the easiest, using my left endpoints or my right endpoints. And so those are the ones we're going to look at. Alright, so for this particular example, I'm going to take my x squared plus 1 over the region 0 to 2. So again, my change in x would be 2, a distance of 2. Suppose I'm going to break it into 4 smaller rectangles. Alright, so I'm going to divide it into 4 sub-intervals of the same width. So I do that by taking my 2 minus 0 divided by 4, and so that means each of my rectangles will have a width of 1/2. Meaning I split this big interval up into 4 little intervals. Each of them will be a distance of 1/2, right? So instead of going from 0 to 2, my first region, so my area 1, would go from 0 to 1/2, right? Distance of 1/2. My area 2 would go from 1/2 to 1. Area 3 would go to 1 and 1/2. Area 4 goes to 1/2, 2. I've still covered the entire region, right? 0 starts, 2 stops. But I've broken it down into 4 smaller subintervals, each with a width of 1/2. What we can do is, well, we can then draw a rectangle over each one of those. Each one of those little areas, I'm going to draw a rectangle on. Now, the problem is there are actually infinitely many ways to draw your rectangle. We're going to look at the 2 easiest cases, using the left endpoint and the right endpoint. Now, the book right now just looks at left only. When they get to 1.7, they look at both. So, again, I'm combining them here in this section. I'm going to do both. Alright, so again, that's why 1.2 just does left, 4.2 just does left, 4.7 does both. So I'm combining them both in this set of notes. Alright, so 2 ways to draw the height. The width is 1/2. The height is, I can either draw it using the left endpoint of my interval or the right endpoint of my interval. Right? Endpoints are left and right. So here's the picture if we start with the right side. right, which again, the book just does left at this point. So just make sure you know that is a little different than what the book does. This is kind of 4.7. They do that in 4.7. Alright, so if I take my original, so again, this is the original graph. There's the red line that represents my function f of x from 0 to 2. I broke it up into 4 intervals, right? These would be my subintervals. There's 0 to my 1/2. There's my 1/2 to 1. My 1 to 1.5. My 1.5 to 2, right? There's my subintervals. There's area 1, area 2, area 3, area 4. Right? Recognized by my intervals. And then what we mean by using the left endpoints, so when I go to draw my rectangle, I can draw it 2 ways. I can either start on the left side, or I can start on the right side. So in this case, I started on the right, which means I start here at 2. The right value would be 2 for each of these intervals. It would be 2 for the first, 1.5 for the second, 1.5, right? Those are all my right side of my intervals, right? Those are on the right side of that, each one of those little, right, if I go back to my intervals here, these are the right values, right? Of each interval, right? 2 is on the right side, 1.5 is on the right, 1 is on the right, 0.5 is on the right. Those are the values that I'm going to use to draw my rectangles, and that's what we did here. At 2, I went up, I drew my rectangle, and the rectangle stops here at the point on my curve. So this would be 2 f of 2. Right? At 1.5, I start here and hit my curve. This would be the point 1.5, f of 1.5. Start at 1, hit my curve. This would be the point 1, f of 1. And then the last graph would be starting here, graphed over. This would be at 0.5, f of 0.5. Alright, so that's what we mean by we use our left endpoints to draw a rectangle. And those left endpoints would be the height, right? This is the height of this rectangle 4. This is the height here. This is the height 2. And this is the height of 1. Alright, so when I draw my rectangle, the y value, the function value, represents the height. Right, so in this case, the height would be whatever h of 2 is, that y value is. Alright, so the height of each rectangle is determined by the function value using the right side of each endpoint. Again, it's nothing more than the function value, so you just plug it in. And so my first rectangle, area 1, would be the 1/2 would be the width, right? The width here is 1/2. The height would be my function value at 1/2. The area of the second rectangle would be 1/2 times the height at 1. The area of the third rectangle would be 1/2 times the height at 1.5. And so again, that's just base times height, base times height, base times height, base times height. We find the base is the same, it's that half a unit. The height is the function value at the correct endpoint. Alright, so then again, where we find those endpoints, remember f of x is x squared plus 1. And so when I take my 1/2, right, I'm looking here, when I take my 1/2, plug it into this function, I get 1.25, right? That's the height of the first rectangle. This height would be 1.25, right? That would be the height, the width would be 1/2. So I take my 1/2, that's 1.25 to find the area of the first rectangle. Then I do the same thing for 1. When I plug 1 in, it becomes 2, right? This height would be a distance of 2, the width would be distance of 1/2, and so on. I do that for each and every rectangle. And so 1 comes out 2, so I take my 1/2 times 2, 1.5 comes out 3.25, and 2 comes out 5. And so there is area 1 plus area 2 plus area 3 plus area 4. And so you multiply those up and add them up. And so, again, I say a high estimate because if you go look at my curve, I've got this extra area above here, right? This would be extra. So it means it's an estimate. My area is about 5.75, and I know that it's less than that, right? Because I've got those little bits of area above. So I know it's close to 5.75, but it also is smaller than that because I've got those areas above. And so that would be the right endpoints. We'll do the exact same thing using left endpoints. Alright, so again, taking right endpoints, the function value is not our only option. And this is the book covers this right now. Again, later on in 4.7 we'll cover the other one. So the left, alright, so now looking at the other side. So if we take the rectangle heights instead of from the right, now we're going to look in the left. So the setup's the same. I divide each region into 4 subintervals, and so these are the same 4 subintervals. Each of them have the same width of 1/2. This would be area 1, area 2, area 3, area 4. But now my areas are going to be drawn differently. This time, I'm going to use my left endpoints. Alright, so again, those would be the left side of each of my intervals. So I'm going to use 0, 1/2, 1, and 1.5. Those are the values I'm going to use. And so I've got that in my next picture. So I start on the left side, so meaning I'm starting here at 0. This is the left side. I go up, I hit my curve, and so my first rectangle's height starts here at 0, f of 0. That will be my area 1. This is still 1/2. And then my second one starts here, so area 2. Again, that's going to be at 0.5, f of 0.5. Area 3 would go here, and again, that would be the height at 1, f of 1. And then my last rectangle starts at 1/2, goes up and hits my curve at 1/2. Alright, and so this time it's going to be a low estimate. You'll see one on the left side. It's just the way this one's drawn. It's just a coincidence in this case. It doesn't always work out this way. But this is going to be a low estimate because you'll see I've got this leftover area here where the green isn't drawn in. But those are the 4 rectangles I'm going to use where I'm using the left endpoints to get my heights, right? This would be height 1, this would be height 2, this would be height 3, this would be height 4, which are my rectangles. Alright. So again, area is estimated by finding the area of each rectangle drawn above and adding them together. And so this would be area 1, area 2, which I forgot my 0.5 here, area 3, area 4. I have to remember it down here. Alright, so area 1 now is 1/2 times 1, right? When I plug 0 into, remember I'm plugging it into the x squared plus 1. I plug 0 in, right? When I get to this point here, it's at 1. So there's my first area. 1/2 times 1, right? Base times height. 1/2 times 1. My second area would be 1/2 times 1.25, right? This height is at 1.25. My third area would be, well, that height's at 2. And my last area would be my height's at 3.25. Alright, and so there's the 4 areas. And so I multiply those out and add them up. And when I add them up, it comes out to 3.75. So in this case, the estimate's a low estimate, an underestimate. I know my area is close to, so I know my area is about 3.75, but I know it's bigger. Alright, so in reality, my area would be less than my first guess, which was 575. And bigger than this one, 3.75. So I know my actual area should be somewhere between the two. And sometimes what you do is you can actually find the average. You take your 3.75 plus your 5.75 and average those out, and those actually come out to be fairly accurate to what the actual area is. But I know it's between those two values. All right, but we're leading to the theory here. All right, so suppose I split it into more rectangles, all right? So instead of just 4 rectangles, I decided to draw 8. All right, so I'm going to draw 8. And I have the picture. I'm not going to go through the process. And I would never ask you to do 8 rectangles. But suppose, okay, again, we're leading to the theory here. Suppose I drew it into 4 rectangles. And so here's the picture from both sides. So this would be the right side, right, using my right endpoints. Then this would be the left side, right, using my left endpoints. And so if you'll see, it's a little better, right? I've got a little less area above, a little less area below, but it's still not perfect. Again, I found those by using the same process we did before. When you add up the right area, so this area up here, the right side comes to 5.1875. The left area comes out to 4.1875. You'll notice those are getting a little closer together. Right? The last examples was 5.75 and 3.75. Well, now I know the area's less than 5.1875, bigger than 4.1875, and so you'll notice there's a little closer, they're a little better, a little more accurate, they're getting nearer to one another. My left endpoints is approaching my right endpoints. Well, suppose I divided into 100 rectangles, and I only drew one side here, because the pictures basically were indistinguishable. So if I drew 100 rectangles, so each of the rectangles would have a very small width. Each rectangle would show up 0.02 distance apart. You'll notice here that it almost looks like I've shaded it in, right? And this was, again, an estimate. This has to be the right picture, but the left picture looked almost the same, so I didn't put both pictures here. But if you look at it, if I did find the left and the right hand using 100 rectangles, all right, using 100 rectangles, my right area was 4.6268, my left area, and so that means the actual area is less than 4.6268, greater than, or sorry, I'm going backwards, less than, I think I wrote those down backwards. It should have been left and right. Sorry about that. Right area, left area. I think I rewrote those backwards. So it should be less than 4.7068, which would be the right area, greater than 4.626268, which would be my left area. Now, I actually found the actual area, and you'll notice that it's pretty close to both those values. The actual area is 4.6 repeating. That's what the actual area is. But now notice that I'm getting pretty close to that from the left and the right. So every time, so again, there's a lot of rectangles in here. There's 100 of them. More and more rectangles I get, the closer and closer I get. So the more rectangles I draw, the closer the left sum gets to my right sum. From the left and the right, I approach the same value. That language should sound familiar. If we make more and more divisions, smaller and smaller rectangles, with the rectangles getting the width, right, the change in x, delta x, approaching 0, right, that delta x approaching, right, when I had 100 rectangles, my delta x was 0.02, that's pretty small. If I had 1,000 rectangles, it'd be even smaller. If I had 100,000 rectangles, it'd be even smaller. Alright, and so what we do, well, if I put more and more rectangles in there, infinitely many more rectangles, that width gets smaller and smaller and smaller and smaller. Approaches 0. It can't equal 0, because if it does, the area zeroes out, right, 'cause it's times 0. But I get closer and closer and closer to it. Well, that language should be familiar to you. That's a limit language, right? And so it is a special type of limit that we solve. Alright, and what we get here is a limit definition. And then right now we're sticking to positive, but when we get the fundamental theorem of calculus, it won't necessarily be positive functions, but it does have to be continuous. So if I want a positive continuous function from a to b, right, so if I'm drawing a function that's completely above the x-axis from a to b, right, f is a continuous function from a to b, the limit of the Riemann sum is that left-hand, right-hand sum that we were finding. All right, for all choices of x, left, right, actually it can be anywhere, middle of the function, doesn't matter. Where we break our a to b interval into intervals of equal width, right, that's my delta x, my rectangles get broken up into smaller and smaller intervals. Then the limit of the sum of the rectangle areas is given by the following. So it's the limit as n goes to infinity. As n goes to infinity, I get more and more rectangles. My change in x goes to 0. Doesn't ever get to 0, but it approaches 0. Of my change in x, my width, times my function value. Right, and those would be using one of the endpoints. Right, those would represent those left and right hand. Delta x is the width, f of x is the height. So it's the width. So those are my rectangles, right? So I've got infinitely many. I'm approaching infinitely many rectangles. All right, that limit is a limit of an infinite sum. And so what this is this is the accumulation. This is the sum of all the function values from x equals a to x equals b. That's what it's literally for. That's why it's an accumulation function. I'm adding up all of the heights, which are my function values, from my starting point to my stopping point. Right? If I look at the picture, I'm going from A to B. What you're doing is you're literally adding up all the heights, right? This would be f of x1 plus f of x2. Now it's times my delta x, but remember, delta x is really small. It's approaching 0. And it can go as small as I want. More and more rectangles I get, right? Going to infinitely many rectangles, the smaller that delta x gets. So basically that height doesn't matter, or the width doesn't matter anymore. I'm just adding up the heights, which are my function values. So I'm adding up. So again, it's an accumulation of all my function values from point A to point B, and that finds this area. Alright, now, later we're going to give you a theorem that solves this limit, this special limit. We do not solve this limit by hand. It's way too hard to do. That would be something you would do in the other calc class and higher level mathematics. So again, we will not be solving, unlike the derivative, we will not be solving this limit by hand. But what we're going to do is we're going to practice doing the Riemann sums, the left and right hand sums. Alright? Make sure you do watch the MyLab videos. They do a good job of showing you how the estimate of the area under the graph works. They do a good job of explaining it, and again, I encourage you to make sure you watch those. Most especially if you're trying to do the homework, because they do things slightly different than what I do. I'm kind of looking at the overall picture. So do make sure you watch those. They do a good job on this. I will do a few more examples, but again, you really need to watch the MyLab lesson videos, both for 4.1 and for 4.7. Right, when we get there, that's later, because I kind of combine them here in one set of notes. Alright, so we'll get to the applications of finding area using geometry and left-hand, right-hand sums. I'm going to stop there.